Hello, everyone. Let's go over the lab for this week. The lab is focused on learning about circuits, and in particular, circuits that have resistors in them, and resistors that are in series combinations or parallel combinations, or both series and parallel combination circuits. So the first question is, what is a resistor? The easiest way to think about a resistor in everyday life terms is a light bulb. When you plug a light bulb in, a tungsten style light bulb, there is a certain material in there that has a certain resistance to it. And as the electricity passes through a resistor, there is some energy dissipated by the resistor. And that energy is dissipated in the form of heat, light, in terms of a light bulb. Um, and all materials have a certain amount of resistance to them. Metals like copper and silver and gold that are really good conductors have really, really low resistance, whereas other types of materials have higher resistance. And so when the electricity and the electrons flow through those resistors, they meet some resistance to them, and that resistance kind of comes out in the form of heat and light energy. So for example, when you turn your toaster on, right, when you look in there after a certain point in time, you see the toaster coils start to light up, they get hot, and so they are emitting energy. And they're toasting your toast. A lot of appliances you use in your everyday life have a resistor in them. And so let's talk about combinations of resistors in my circuit. Let's first talk about a series combination. So let's suppose I have a battery, and I'm going to denote the battery like this in my circuit. One side is longer than the other. That is indicating that this is a higher potential, this is a lower potential. So if this was a 9-volt battery, this side would be provided 9 volts, and there's a potential difference across here of 9 volts. So this side of the battery is at 0 volts. And sorry, my cat just jumped on my lap. And so let's put a couple let's just put one. Let's start with one. So let's just suppose we have one light bulb connected to one 9-volt battery. And the way we denote resistors in the circuit diagram is through the squiggly line. And so the current is going to flow here. It's going to come out of the battery and flow through the circuit. Now with current, current and charge are conserved quantities. So like if there's 10 ohms of current coming out here, there must be 10 ohms coming back into the battery on the other side. You can't have like a difference in current somewhere here, because that would mean that you're losing charge somehow, right? But all of the charge is in this circuit. So if there's 10 amps here, there's 10 amps here, there's 10 amps through the resistor, there's 10 amps here, and there's 10 amps here. There's 10 amps everywhere in this circuit. And let's just say that this resistor has 9 ohms of resistance. And resistance is measured in ohms, and the symbol for ohms is this funny looking Greek symbol. So if you remember Ohm's law, it tells us the relationship between the voltage, the current, and the resistance in my circuit. I only have one resistor here. And I have the voltage across that resistor is 9 volts, right? This side of the resistor is connected to the 9 volts. This side of the resistor is connected to the 0 volts. Okay, so there's a 9-volt drop across this resistor. And so if I apply Ohm's law here, V equals I R, I have 9 volts of potential. If I want to know the current, I can use this, and the resistance is 9 ohms. So I made it simple here, and if I solve for the current in this particular circuit, it's going to be 1 amp of current. The connecting wires, the connecting conducting wires in our circuit are things like copper, silver, gold, whatever. They're really, really, really good conductors. And so they really have low resistance. So we don't take them into account, right? They're just like connecting things, right? But there's no voltage drop across these conducting wires because we're just going to assume that they're perfect conductors and there's no voltage drop across them. The only voltage drop is across the resistor. And so if I plugged a 9 ohm resistor into the circuit, connected to a 9-volt battery, I would get 1 amp of current. Now this would change if I changed the ohms here, the resistance. Maybe I'll make it 1 amp. 1 ohm. Okay. What's going to happen to the current? Obviously, it's going to go up. I have less resistance here. There's less resistance to the current. So if I use Ohm's law again for this one, you'll see that if I use 1 ohm resistor, my current is now going to be 9 amps. Oops, that's not what I want. A lot more current flowing with less resistance. Now let's say I had no resistor here at all. Maybe I just had connecting wires. And if you've ever done this with a battery and you've just connected a copper wire across the ends of the battery, you probably have noticed a couple of things. The first thing is that the wire gets really, really, really hot. And another thing that will happen is that you will wear your battery out very, very quickly. Why? Because we now have very little resistance to the circuit. If these are, copper wires, they have very, very little resistance. So this resistance is tiny, right? Tiny little resistance. I have, a certain amount of battery voltage, 9 volts, whatever it is. This resistance is really, really small. What's going to happen to the current? It's going to get huge, right? To maintain 9 volts. So I have a huge amount of current flowing. And when you have a huge amount of current, that means there's a lot of power output. There's going to be a lot of heat generated, and potentially you could melt your wire. It could get so hot, but your battery will also run out very quickly too because you are running so much current through your circuit. This is called a short circuit. There's no load on it. And so this is a bad thing to have actually in your home, right? You would think, oh, I don't want that much resistance. Well, actually you do want some, because if you don't have any resistance or very little resistance, you're going to get a lot of current flowing, and that's not good for your battery. And it's also not good for your house, right? If you've got a short circuit in your home and this wire is getting really, really hot, there's a potential for a fire. So that's another thing you will explore in the lab today. Let's just go over one more example with resistors in series. So let's look at 2 resistors now in series. And by series, I mean they are one right after the other with no breaks in the circuit in between them. There's nothing else in between them, right? They're connected one right after the other. That's what we mean by a series connection. And again, let's say this is a 9-volt battery, and this is 4.5 ohms, and this is 4.5 ohms. If you have resistors that are in series with each other, right, one right after the other, because they are one right after the other, the same current has to flow through each one. There's current flowing from the positive end of the battery. It's hitting this resistor and then it hits this resistor. They both have to have the same current going through them. Because if they didn't, that would mean there's current like going out here somewhere, which doesn't make sense, right? So they have the same current flowing through. And let's determine what that current is. If you have resistors in series, it's really easy. You can find the overall resistance of the circuit in series by just simply adding them together. So because these are back to back, one right after the other in series, I can just add these two resistors together and I could create an equivalent resistance, which is simply 9 ohms. So I could take these two resistors, combine them into one, and it would be a 9 ohm resistor. And it's causing the same current as the two 4.5 ohms back to back. So whether I look at this circuit or this circuit, they're equivalent. And so now I can go back and use Ohm's law again and solve for the current here, which would just be 1 amp. So resistors in series are pretty easy to deal with, right? You just add them up and then you can find the equivalent resistance and find the current from there. If I wanted to know the voltage drop across each one, okay, this one has 1 amp. I don't want that. This one has 1 amp flowing through it. This one has 1 amp flowing through it. The battery has 1 amp flowing through it. These are all in series with each other. They all have the same current. I can use V equals IR for each individual one. And so that means that the voltage across this resistor will be 1 amp multiplied by 4.5 ohms. 4.5 volts drop across this one, and 4.5 volt drop across this one. That makes sense because remember, in a circuit, all of the potential increases from the battery have to be equal to all the potential drops across each thing in the circuit. These two, this one is 4.5, this one is 4.5. It's a total of 9 volts. And then there's a 9 volt increase from the battery. So everything is balanced out. It's really just energy conservation ultimately. You have an increase of 9 volts and a decrease of 9 volts in your circuit. So it's easy to check your work and see if it's making sense because all of the potential drops due to the resistors should add up to the total potential increase due to the battery. If I added another resistor into the mix, what would happen to the current? It would go down, right? And as I add more and more resistance to this circuit in series, the current would keep going down and down and down and down. You have more basically load on your circuit here. If these were light bulbs, each light bulb would become dimmer and dimmer and dimmer as I added more and more resistors to my circuit. It's like, yeah, it would just keep getting dimmer. So that's resistors in series. Let's now focus on resistors that are in parallel with each other. So when resistors are in parallel with each other, what that means is, here's my battery. What that means is I'm taking my battery and I'm connecting them. I'm connecting the battery to each individual resistor separately. So the ends of each resistor are each connected to the battery. Okay. you can connect the ends of each resistor to each other as well, right? See how they're all connected here and they're all connected here, right? And if this is a 9-volt battery, there's a 9-volt increase here. That means that on this side of all of these resistors, there's a 9 volts of basically energy. And if I look at this side, on the other side of the resistor, they all have 0 volts because they're all connected to the 0-volt end of the battery. So each resistor has a 9-volt drop across it. So in parallel, they all have the same voltage drop across each one. Now, we don't normally draw it like this, but this is ultimately what's happening. The connecting wires are just there as connectors, right? They're not doing anything. So you're basically just putting 3 resistors across each one. Each resistor is across the battery, and it's getting the full voltage of 9 volts. The way we normally draw resistors in parallel, like in the textbook, it looks something like this. So let me draw it over again. Here's a 9-volt battery, and I can draw it like this. This is the same configuration as what I just drew. I just added more connecting wires. But ultimately, I could just take the end of this battery and it's connected to this one, it's connected to this one, and it's connected to this one. Same thing on the other side, 0 volts connected here and here and here. It just looks prettier this way. So let's make it simple for ourselves and make each of these, I don't know. I'm just gonna stick with, no, let's go with 3 ohms on each one. Notice that each one of these resistors is getting the full amount of the voltage. And so if I wanted to know the current through this top resistor, V equals IR, right? The current is going to be its voltage divided by its resistance. The voltage across this 3 ohm resistor is 3 volts. Notice that it's connected to the battery. It's got the full amount of voltage. So I'm going to put 9 volts on the top, 3 ohms on the bottom. And so this is getting 3 amps of current running through it. And we could do a similar process with the other ones. This one has 3 amps and this one has 3 amps. Now they all have the same current because they all have the same resistance. If these were different resistors, they would have different currents running through, right? The largest resistor would have the least amount of current, and the smallest resistor would have the most amount of current running through it. Current kind of always wants to follow the path of least resistance. So if it can find a path that has no resistance, all of it will go that way. But if there's a little bit of resistance, it will still be current running through there. But yeah, so each of these has 3 amps. And if you think about it, if there's 3 amps coming in at this junction, there's 3 amps coming in here, and there's 3 amps coming in here, there must be 6 amps coming here, right? And there's a 6 amp and then another 3 amps here, so there's 9 amps coming in here. There's 9 amps running through the battery. So that's how you can kind of think about current and resistance for resistors that are in parallel with each other. And if you wanted to find an equivalent resistance for these 3 that are in parallel, It's a funny equation. It's the equivalent resistance, 1 over it is equal to 1 over each of the resistors in parallel. So this is the equivalent resistance for parallel connections. And if you solve for this here, R1 would be 3 amps, R2 would be 3 amps, R3 would be 3 amps. And if you solve for the equivalent resistance, don't forget to take the inverse here because it's all of these are inverted. The equivalent resistance would be 1 ohm. So it's interesting that as you add more resistors in parallel, what you're actually doing is decreasing the overall resistance of your circuit. It seems weird, but that's what it's doing. Because ultimately, as you add more and more resistors in parallel with each other, you're increasing the amount of current that is being supplied by the battery. And so that is overall decreasing the equivalent resistance. And so I have a question for you. If these were light bulbs, all of these light bulbs would be the same brightness. Do you agree with me? It makes sense. They all have the same current running through them. They all have the same voltage across them. They're all the same resistance, right? If I added another resistor to this in parallel, and let's say it was a light bulb, and let's say it was a 3 ohm light bulb, what would happen? How would the brightness of the light bulbs change? Think about it for a second. The answer is that the brightness of all of these light bulbs would not change. They would all maintain the same brightness. Because if I add this 3 ohm resistor down here, it is connected in parallel with the battery, so it's going to get 3 amps of current through it as well. It looks just like the other light bulbs in the circuit, so it's going to have the same amount of brightness as these. So adding another resistor in parallel, they all would have the same brightness. That's different than series, because remember in series, as I added more resistors, they kept getting dimmer and dimmer and dimmer, right? In parallel, they all maintain the same brightness because they all maintain the same voltage across each one. But what would happen to the overall resistance of the circuit? It goes down as I add more resistance in parallel. The overall resistance goes down. So the current would go up. Now I would have 3 amps coming in here, 3 amps here, 3 amps here, and 3 amps here. Now I'm having 12 amps being supplied by the battery. Okay, so in parallel, as I add more resistors, the current that is being provided by the battery increases to maintain the same amount of voltage across each one. Our homes, this is an important takeaway, our homes are wired in parallel. Okay. Every time you plug something into the wall, we are getting the full 120 volts, right? that the outlet is supplying. But if you've ever had a problem where you plug too many things in at the same time and you're blow your circuit, this is the reason why. Because let's suppose one of these is my toaster, one of these is my coffee maker, maybe my oven is on, my refrigerator is running. I have so many appliances running in my kitchen, and as they're all running, what's happening? That means that the current supplied by the circuit in your house is increasing, right? And there's a maximum amount of current that it can supply, right? Because we said as these connecting wires get more and more current, they're going to get hotter and hotter and hotter until eventually they could potentially have a get too hot and melt, right? So that's why you have a circuit breaker that shuts off at a certain amount of amps. Because if it goes above that, there's a potential for overheating the wires. Okay. But if our homes were wired in series, it wouldn't be good, right? Because I would have, maybe my lamp is here, my coffee maker's here, and my hair dryer's here, or whatever, right? And they're all in parallel. Let's suppose the light bulb burns out and this thing breaks, right? Is the current going to be able to keep going here? No. If this resistor is broken, right? It's broke, right? And current can no longer flow through it. That means current can't get to the other things either. So it wouldn't make sense to have our homes wired in series. Now, there are certain appliances or electronic equipment that needs to have the circuit coming in. Um, Never mind. I'll get to that later. We'll talk about that later. But that's the idea, okay? So let's take a look at the circuits lab, and we'll just show you what you're going to be doing. So you're going to be testing all of these ideas in the circuit lab. So in the first part, you're going to do resistors in series with each other. You'll do 2 resistors in series with the battery. You'll do 3 resistors in series with the battery, and then you'll check and see how it would look if they were light bulbs. So let me open up the simulation so you can see what it looks like. When you click the link, it will when you click the link, it'll bring this up first. You want to click on lab. And let's create a circuit. I actually suggest that you use this throughout the rest of the semester because this is a great simulation for you to just play around with and see what happens. So let's build a circuit, right, with 2 resistors. I like to put a switch in. It's pretty intuitive, right? You just kind of connect the wires together, and the resistors are here, so let's put 2 of them in. Like I said, you don't really need to have these wires. They're just there to kind of help you visualize things better. All right. And if you want to change anything, you just click on the circuit element. So the battery right now has 9 volts. You can increase it up to 120. Let's leave it on 9 though. That's a pretty common voltage. Oh my gosh. Okay. And each resistor, 10 ohms here, 10 ohms here. That's fine, right? You can change it around if you want. You can do different resistances if you want. It doesn't really matter. What you're going to do is, let me go back to the lab. So you will plug in resistor 1's resistance, which was 10 ohms. Resistor 2 also had 10 ohms. The battery, we're going to assume, has very little internal resistance to it, so it doesn't have any resistance. Now, let's determine the current and the voltage across each one. First of all, make a prediction. Okay, do the math first. I promise you, please do the math first, like we just did on the whiteboard. Okay, and check what is the current running through R1? What is the current running through R2? What is the current running through the battery? And also predict what the voltage should be for each one. Obviously, the battery has 9 volts. And then go back to the simulation, run it, and see if your answers match up. So to see if your answers match up, what you can do is, I'm going to close this, right? So here we see the electrons are flowing here. And if you want to measure the voltage across each thing, you just pull out the voltmeter. And it's really easy. You just put the probes on either side of the thing you want to measure the voltage across. Obviously, the battery has 9 volts across it. the resistor 1 has 4.5 volts. The second resistor has 4.5 volts across it. It makes sense. 9-volt increase across the battery, 9-volt drop total across each resistor. If you want to measure the current, pull out the ammeter. Ammeter is a word for a tool that measures current. Just pull that out and then just put the probe anywhere you want to measure the current. 0.45 amps there, there, there. It's the same throughout the entire circuit because everything is in series with each other, so they all have the same current. And when you're done using the tool, you can just drag it back over. It's really intuitive, I feel like, anyways. Let's keep the wire resistivity and source resistance tiny so we don't have to worry about that. So that's the idea. I suggest you make the resistors different resistances. It's a little boring if everything's the same, right? So obviously if I make this thing huge resistance, this is going to make the current even slower, right? So just play around with it. You know, it really helps you learn about circuits when you play around with this. The other part of the circuits lab asks you to do resistors in parallel. Okay, so again, just create your circuit with 2 resistors in parallel connected to the battery and make a prediction as to what you think it should be. And then check your prediction using the simulation. Make the prediction first and then check it, right? And so to do that part, again, it's pretty, I know that there's a way to delete these things. Okay, yeah, to delete it, just click on the circuit element and then trash. Sorry, a little tedious, but and by the way, these are actually what resistors look like in real life. If you actually look at one, they have these bars on them, and each bar kind of tells you how much resistance it has. Different colors mean different amounts of resistances. So let's put our battery in. I like to put a switch. You don't have to, but I like to put it there just so I can turn it off and on. So I'm going to make our resistor here. And I'm going to put another one in parallel with that. So I'll put it down here. Make sure that all of the connections are there. Sometimes if it's off, it doesn't, you know, obviously it's not going to work. So make sure everything is connected. And, you know, change your resistance on each one. Make it different so you can see. Oh yeah, and as you change the resistance, the colors change on here. So the colors are referring to how much resistance you have. So this one has 13 ohms. This one has 40 ohms. The battery is a 9-volt battery. Make a prediction, first of all, which one is going to have more current, which is going to have less current. Let's close the switch. Notice that in this branch, the electrons are moving really slow. That's because this one has so much resistance, right? They're not going to be moving very fast in this branch of the circuit. This one has less resistance, so the current is able to flow more quickly down here. And when they get to the junction, those two currents add up together. Let's determine the voltage across each thing. So this one has a voltage of 9 volts across it. How much voltage is going to be across this one right here in the middle, this resistor? It's 9 volts, right? Because it's connected in parallel with the battery. Similarly, this one down here, 9 volts across it. All right. Let's look at the current going through each branch. Now you should make a prediction as to what the current is, but this one, very low current, 0.22 amps. This one, little bit higher, 0.69. The current running through the battery should be the sum of those two, which it is, 0.92. So that's the idea behind the lab. The other parts are combination circuits. So there's a couple combination circuits. What you're going to have to do is find the equivalent resistance for these combination circuits and then determine the current and the voltage across each resistor and then check it using the simulation. And when you have a combination circuit, basically you just, look at it and say, oh, these two are in parallel with each other, so I will find their equivalent resistance. And then when I do, these two will be in series with each other and I can find their equivalent resistance, and then I can find the current. And then you kind of work backwards. If you need help with that, please set up a Zoom meeting with me. But the book should have a couple of examples of combo circuits for you. And then in part 4 is a short circuit. So you're going to look at the circuit and identify the spots where you have shorts in your circuit. And those are spots where there's zero resistance. So I'll give you one answer. If this is the battery, right, and the electrons are flowing, when it gets to this junction right here, there's 30 ohms of resistance here, but there's no resistance down here. So guess what? All of the current is going to flow around here, and none of it is going to flow through this portion. It's going to follow the path of least resistance. So if it can go through a path with zero resistance, all of the current will go through that path. There's another short as well. You will need to find out that. And construct the circuit and look at how the current flows and see if it matches your prediction for the short circuit. And then there's a concept question at the end. No graphs here. Mostly I just want you to think about resistors in series, in parallel, and combination, and think about if these were light bulbs, right? How would the circuit look, right? Because I think if you can explain it using the light bulbs, you've got a pretty good grasp of it, okay? I hope that helped. Please set up a meeting with me if you need additional help with circuits. These can get a little bit tricky, but I think if you got the concept down pat, that's the most important thing for me. So again, email or Zoom me if you ever need any help with anything, and I'll talk to you soon. Bye.